So we finished up chapter 6 last time, and the last thing we did was kind of a visual representation of fraction division, right? And when you start talking about fractions, it gets really weird to try to come up with physical interpretation. So I kind of came up with some of my own. You can kind of like play with it and come up with some others. But so when I say physical, I mean like word problem, right? A visual representation is not as hard to come up with. So let me see if you guys remember how we did this. If I wanted to divide 6, I want to divide it by 2/5, let's say. Could you guys do that visually? Do you guys remember? It's like a whole weekend in the middle, so I don't know. So how do you represent 6? That one's pretty straightforward. How do you represent 6? What do you draw? You want to represent?
You could do like 6 or something. Like 6 of those.
6 what?
6 holes.
6 holes? All right. Yeah, okay, I see what you mean. So let's do like this. Come back over here. There you go. Pour a little marker. Then what would I do?
You divide the holes into bits.
Kind of makes sense because 6 divided by 2 mean, one fundamental way to look at that is how many 2's fit into 6, right? And that's why the answer is 3, because 2, 2, 2 makes 6. You can look at this the exact same way. It's just we're not used to building things based on fifths. We're used to building things based on ones, right? I kind of keep coming back to that idea of it kind of makes sense we build based on ones because that's how we first started to count any damn thing. 1, 2, 3, right? But, so like you said, we cut each of these. Why did I have to pick? Oh, well, too bad, Jeff. And hopefully, if your student was doing this, they might do a better job than I just did. And a real quick way, I'm sure you guys have picked up on this, but if I want to cut something in fifths, I got to make 4 cuts. Do you understand how that's related to an earlier bonus question? Do you guys remember that question about it takes so much time to cut something into so many pieces? So if I want to cut into 5 pieces, I actually just make 4 cuts, right? So now, if I want to divide this by 2/5, what do I start looking for? Yeah, so if I find, so this is 2/5, correct? So there's 1. This is also, so let me do it like this. This is 2/5. This is 2/5. So there's 2. Y'all with me? And then this is 2/5. That's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So it's actually, and again, you can take this and make a physical operation out of this. If I had 6 loaves of bread and I want to give each person 2/5 of a loaf of bread, then how many people could I give that to? 15, right? You guys are kind of with me. So I think you all would agree with me that working mathematically with fractions is not as intuitive, or maybe even intuitive at all, it seems, especially compared to working with whole numbers, right? Why is that true? Because we work with fractions a lot less than with whole numbers, especially if you're a little person, right? You're much more used to working with whole numbers than with fractions. So how do you check this? Is that the right answer? Did I get the right answer? And of course, how do you do this mathematically? What would you do? Yeah, how do you divide fractions? You multiply by the reciprocal. 2 goes into 6. 3 times 5, 15. Crazy sauce. All right. So it's a really nice visualization of what this means, right? So and again, just to harp on this a little bit, 7 is 7 ones. That's easy to see. But 7 is also 14 halves, right? So fractions just kind of remind us we can keep subdividing something and make wholes based on those subdivisions instead of on ones. Okay. So this is kind of like the last thing we did. So let me ask you guys to try a couple things out. Yeah, let's see. How about this? Let me ask you this. So already got this here. Nothing too major. Kind of looks like a old train taking the circus coming to town or something. Okay, especially the way I drew like wheels. Can you figure out what's a good one, Jeff? You can do it, buddy. Yeah. Sure. What this is based on missing factor approach. So I want you to use the missing factor approach. So first off, you gotta remember what the hell missing factor approach means. Yeah. So with subtraction, you have like the missing add-in approach. So 6 minus 2, you think of 6 equals 2 plus what? The missing add-in. Very similar thing we do with the division. Because this is supposed to be the number that when I multiply it by 15/4, I get this. So then you basically think to yourself, okay, what do I multiply 15/4 by to get 45/16? And what's really, I obviously picked really nice numbers here, right? So what would you multiply the top by to get 45? 3. And then the bottom, of course, 4. Okay. Yes?
Why don't you flip since you're going from like division to multiplication, why don't you flip the or do you have to?
Well, here's the idea. I'm not really going from division to multiplication. I am rewriting the problem. So so it's exactly here. Wouldn't I multiply both sides by 15/4 is one thing I could do. So again, why is 8 divided by 2 4? Because 2 times 4 is 8, right? So if you say 8 divided by 2 is a number, that means that 8 is twice some number. So that's exactly what we did here. I like it. Okay, cool. And this kind of illustrates the shortcut when the numbers all work with each other. So we saw this earlier in this section was 45 divided by 15 is 3. 16 divided by 4 is 4. So if the numbers all kind of like work with each other, everything's beautiful, right? I don't know if you guys agree with me or not. No? These numbers work with each other. If I would have made this a 17 and this a 7, then I'm kind of screwed. The numbers don't work well with each other. We need more advanced ways to look at this. Okay, maybe. Okay. All right. What was the other thing? No. Yeah. Something else that happens a lot. Let's see. So you guys help me out. What's 2/5 times 11/17? How would you do that? Yeah, just multiply straight across, right? And again, we did take the steps to kind of build our understanding up. And of course, I know we're all good, but thinking in terms of the students, you want to get them to a point to understand why multiplying straight across actually makes sense. Because it's not immediately obvious that that should work. So yeah, you get 22 over 85, 11. Cool. Now, what I always get is somebody will, if I give them this problem instead, you can do it, Jeff. Sure. Times. Oh, let's do, sure. I like it. What the shit? Now, if obviously one right answer would be just to multiply straight across, because that's how fraction multiplication works. Why is that not the greatest idea here? Yeah, at the end, I'm going to want to reduce this sucker. So I try to show people, before you let the numbers get way big and make the reducing problem difficult, reduce first, right? And we talked about why this makes sense. It's because if I do multiply the top and the bottom, I can use commutativity to turn these around, and then these two can reduce and so forth. So instead of doing all that, if it's on the top and the bottom, I can cross reduce, right? So what happens here? What goes into both of those? 11. What about these? Shit. Say again?
19.
Yeah, 19 will go into both. How many times?
3.
So then what's the answer? 2 nights. I love it. Kick ass. Okay. And that you would get the same answer if you multiply that crap out, but then you get these huge numbers that you have to try to figure out how they reduce. Much easier to reduce smaller numbers before they get bigger. All right, I like it. So as you're teaching people how this works, you get them to understand this, and then they might kind of balk at, well, why can't I? And then you say, yeah, you could. You totally could. Of course it'll work. But I'd much rather lose some numbers in the first place, right? Okay, I like it, I like it. All right, so nothing too amazing there. I thought there was one more thing I wanted to call back, but oh, okay, yeah. I do want to point out one thing on page 241. I don't know if I noticed this, but they do. Remember when I proved to you why we multiply by the reciprocal? And everybody was so excited about that. So I had to make it worse to show you why multiplying by the reciprocal works. So in the process, I always get a student who doesn't understand what my point is. And I'm like, why are you making it worse? All right, this is what math teachers do. And I'm like, no, it's got to look worse as to explain why the shortcut works. So I think I told you this last time. There's so many shortcuts in mathematics, and there are a lot of math teachers that just teach a shortcut. And if you do that, you're not laying any foundation for the student to build on. Does that make sense? You need a foundation on which you can say, oh yeah, because this, there's a shortcut. But they still have this, right? I'm not even sure if this makes sense to you. So trust me, after teaching a lot of different levels of mathematics, you start to realize the through line of if they don't get this at this level, they'd have nothing to build on to get this other idea later. So when you're teaching a student a topic, you have to think about what are they going to be trying to do in the next grade, right? And what do I need them to just understand fully before they get to the next grade? Are you guys kind of with me? So for example, it's really rough being an adjunct instructor, especially when you're first starting off, because sometimes you'll just get whatever courses are left over. And when you're first starting off, you've never taught, and I know I'm talking about college, but it's the same kind of idea. You've never taught the higher levels. You're just teaching whatever the hell they gave you. So you have no direct, you've taken the courses yourself, but you've kind of forgotten, well, what is it really important that I'm teaching in this course that they need for the next course? You don't have that understanding. So for you guys, you all know how all the math works, but you have to know what's coming in the next grade so you can make sure to hit the really important things. Okay. No, that was that. All right, I'll be okay. So, in the interest of time, I did not make a little like handout. I'm just going to get into chapter 7. I think we're just going to make it through to 7.2 for the next test. So don't forget, like, this next test is going to start at 5.2, right? And so it's going to go to 7.2. Are you guys all with me? It was supposed to go to 7.4, but reality, so we're going to go to 7.2. So let me ask you this, to get into this next chapter. Can anybody just tell me, do you have something about decimals that you don't like or don't understand? Or what do you think of when I say decimals? Obviously, you can imagine a decimal. But is there anything about the decimals that comes to mind specifically? Like, how it's been a long time since you had to add decimals by hand, correct? Yes.
Like changing decimals back to fractions.
Okay, beautiful. All right, I love it. This is what I want. So changing decimals to fractions. Kick ass. Anything else? So there's a connection between fractions and decimals. So here's something kind of freaky. Let me ask you this. How do you say that? And some of us will say, you say 0.12, Jeff. What's a little more technical way to say this? Does anyone know what place that's in? And you're like, in this place, in this room. This is our time. No. Yes?
Is it in the hundreds?
Maybe. Yes. So real quick, just to make up something. What place is this? Thousands. Right? And then what place is this, of course? Hundreds. What did it do to 1,000 to get to the next place? Divided by 10. And it makes sense. Our number system is based on 10. There we go. And so every place is going to represent another multiple of 10, right? We've talked about that back when we did Babylonian and all that kind of business. Okay. So I divide by 10 and I get hundreds. So not surprisingly, the next place is tens, because I divide by 10 again, and then divide by 10, so this is ones. Divide by 10 again, tenths. I love it. Then you start to get a lisp, right? A little lisp. Tenth. And this is hundredths. Yeah, good job, Joe. Hundredths. Okay. So I want you to realize something. Fractions are just, decimals are just fractions that fit into our base 10 number system. Can somebody give me a fraction that could become a decimal, a terminating decimal? So I'll start. There's one. So 12 over 100 is automatically, yeah, 3/4. 3/4 works. So you don't have to have a 10 on the bottom, correct? There is something that's necessary. Doesn't the bottom, in order to go into decimal, in order to go into our number system directly. And what do I mean by that? There's a place for each digit, and so these digits mean something very specific. They mean certain types of fractions. Is that cool? This one means so many tenths, so over 10, over 100. But does the fraction have to have a 10 or 100 on the bottom to become something that will fit into our decimal system? No, it doesn't. Why does 3/4 work? Y'all know what 3/4 is. What is it? 0.75. Why? What is 0.75? Directly. What place is that in? Tenths, hundreds, so 75 hundredths. Right? And of course, how do you go from there to there? Well, you multiply by 25. Is that cool? So watch this. So you guys, I really want this next thing. This is kind of cool, this next thing, because I didn't even think of it. This is so interesting to me. Until the first time I taught this class, I had never thought about it in this way. This works because it's got 2's on the bottom. Watch what do you have to multiply by again? 2 5's, right? 25, which is 5 times 5. Are you guys with me? And do you see how if I multiply by 2 5's, it makes 10 and 10. 100, right? All right, let me stop right there for a minute. So, if the bottom has any number that is not a 2 or a 5, and it's already reduced, it's screwed. It can't become a terminating decimal. Let me say this again. If the bottom, for example, if I have 1/6, 1/6, can that become a and I keep saying this, I don't want to make sure you guys are with me, terminating decimal? Why is that terminating? Because it stops, right? Okay. So everybody with me? So of course, eventually we're going to talk about non-terminating, and you guys already know at least one non-terminating decimal. Why will that not become a terminating decimal? What's on the bottom? 2 times 3. It's got a factor of 3, correct? I really want this to make sense. In order to become a terminating decimal, what must be true about the bottom? Only made of 2's and 5's, but more kind of like on a less granular level, it's got to be some multiple of 10. You got to be able to make it a multiple of 10. You guys all agree? So let me ask you this. Let me keep this here. We'll talk more about this. Can somebody tell me what that is as a fraction? And then I'll show you a shortcut. But for now, I'm going to make you guys. All right, how'd you get there? What are you doing? So you can try to do tenths, hundredths, thousand, right? You can just kind of like say the words, the little chant. And that'll be fine, as long as you kind of keep track. But I use that word when I shouldn't. Here's an interesting kind of idea to realize. What is 1/10? How do you write this as a decimal? 0.1, 11. How many decimal places are there? 1. How many zeros are there? Interesting. What about 1700ths? How would you write that as a decimal? 0.17. And real quick, just to really make sure you guys get this. This is 1700ths, which means the last digit needs to be in the hundredths place. Just like, how do you write 34,000? What number has to be in the thousands place? 34,000. What number has to be in the thousands place? The 4, right? So the last digit has to be in the place for the word that I'm saying. So 1700ths, the last digit has to be in the hundredths place. Hundredths. I got to make it a harder lift. Okay. So I can kind of extend this idea. It's really beautiful because the bottom is all powers of 10. I just have to go 1, 2, 3, 4, 5, 6, 7, 8, right? 9. So the 2 is in the 9th decimal place. So how many zeros I'm going to have after the 1? 9. So you can either count your way there by the chance, or you can literally count your way there. Can we stop for a minute? Since the bottom either has to start as or be able to become some power of 10, there can't be any other factors on the bottom besides 2 and 5. Does that make sense? If I only want the bottom to be some power of 10, and 2 times 5 makes 10, It can't have any other factor down there. So 1/6 does not work because it's got a factor of 3 in there. And sure enough, what is 1 divided by 6 if you try to do it? What do you get? My hand still doesn't operate as a calculator. Some of you guys turned your calculator back in, I'm sorry. 1 forever, right? Okay. One non-terminating decimal that I know you guys know. What is 1/3 as a decimal? 0.3333. Okay. I can't remember if this book does this. Isn't 1/3 3/9? So isn't 3/9 also 0.333, right? Okay, so what is 1/9? Yeah, totally. 3/9 divided by 3, so 0.33 divided by 3. So what's kind of nifty about that is what's 2/9? It was 7/9. Okay. So a lot of the fractions that have patterns to them are divided by some kind of either a multiple of 9 or a multiple of 3. See there? 6 is a multiple of 3. That's 0.1666666 forever. It's got a pattern. Okay, maybe. I kind of want to show you this. I don't know if you guys are going to freak out. Let's see what happens. Let's see. What's another? Yeah, sure. What if I want to know? Yeah, okay. What if I want to know like 0.2727 forever? And I'm drawing that. I'm pretty sure you guys understand that the bar means what? The thing that it's covering continues forever. So that's 0.27272727. Let's say I want to know what that is as a fraction, right? I'm not sure if you've ever seen this. Does anyone know what that is as a fraction? It's okay if you don't, it's fine. Because does anyone know? Tell me. No, okay, good. So in algebra, if there's something we don't know, what do we call it? Something we don't know in algebra, we call it x. I love it. So I'm going to call this x. Why does that decimal, why is it harder to write as a fraction? What would have been an easier one to write as a fraction would have been like 0.27. If the damn thing stopped, that would be easy. Any decimal that stops is easy, period, to write as a fraction. Easy. Everybody agree with me, right? So this one sucks because it goes forever, but at least it goes forever in a repeat, in a pattern. So watch this, it's kind of cool. And let me know if you've ever seen this before. What really sucks about this is all the infinite 27, the infinite 27s, right? So watch this. What do I get if I multiply both sides by 100? What happens to a decimal when I multiply it by 100? The decimal moves over twice, right? And why does it work like that? Because it's based on 10. So when I multiply a base 10 number by 10s, that should be easy because they should go together really nice. So this would become 27.2727 forever, right? So I'm sneaking a little bit of algebra in, but I think we're all cool with it. So watch what happens. How do I make the infinite 27s cancel? I just subtract. 100x minus x is 99x. Is that cool? And what's 27.27 forever minus 0.27 forever? The 0.27 forever is just cancel. So this is 27. So then I just divide by 99. And how do I reduce that? Yeah, divide by 9. So I get 3/11. like it. So 3/11 is 0.2727 forever. All right, let me see if I can push my luck. What's 1/11? What do I do to go from here to here? I divide it by 3. So if I divide by 3, what's 27 divided by 3? 9. What's 27 divided by 3? 9. So if you have a calculator, do 1 divided by 11, and you'll get that thing. Yeah, I like it. Let me stop for a minute. You guys ever seen that before? Okay, you could do a similar thing with 0.333 forever, or 0.111 forever. But we already talked about this. Okay. What about how do I say that? How do I actually say it? First part's easy, right? Or maybe it is. Let's see. It's a little thing we got to be careful about. If you ever written a check, you know exactly how to say this.
3,416.
Careful. I think I heard it sneak in there. There's a little thing you got to be, it seems too picky, but the and specifically needs to indicate where the decimal is. So if you've ever written a check, you basically 3,416, 3,416 and 79 hundredths, right? Okay, cool. All right. So nothing major there, but that's kind of nice. The check writing kind of reinforces that idea. Okay. Oh, I did that early. That's right. Now let me show you something we've seen before, but I want to see if you guys can figure out how to repurpose these things. Oh, that's right. Oh, yeah. That's right. Turn on it so it can be sure to blind me. All right, so these guys. Okay, let me see. No, I won't be the other way. All right, that's as far out as I can go. Okay. You guys remember? Let me put this guy down. All right. The way we used these before was. This was obviously a unit. This represented 10, 100, 1,000. How can you repurpose these to actually talk about decimals? So how many total are in this guy? There's 100. So what would this represent in this? 100. I love it. Now the thing you gotta be careful about is what would this represent? 1/10. I love it. And of course, what would this represent? He still represents 1. I like it. You can always guarantee there's always going to be a 1 somewhere. Okay. You guys understand? So I could, how would I use this to represent 7/100ths? So remind me, what was 1/100th in this thing? One of these little dudes, right? So one way I could do this, and I thought we had, there's something that looks sort of like a weird-ass ice cube tray, where they're like little holes. But one way you could do this is just start putting down, if I just put 7 of these suckers down, that would represent, see if Jeff can count today. I think he can. Excellent job, Jeff. That would represent 7/100ths. Are you guys with me? You guys 7 with me? Okay. So real quick, what is this? better? A little bit. Okay. Say again, sorry.
110.
All right, all right, so I love it. If you go along with what we were doing, that would be 10 tenths, right? 4 little 2. That's 10 tenths. If I counted correctly, did I? Yeah. But, again, each of these long dudes is actually how much of this? 1/10. I love it. So, this would be 10, I said that wrong. This would be 10 hundredths on this, which we know it reduces to 1/10, but this is a nice visual. 10 hundredths is the same thing as 1/10, right? Each long would be 1/10 of the entire thing. Okay, I like it. So that's sort of a weird thing sometimes for some students to get is I can just add as many zeros on the end of this as I want to, and it represents the same number. That is definitely weird. Because at this point, they're used to saying, okay, which one's bigger? Well, that one's bigger, right? But now if I do this, which one's bigger? Which one's bigger? They're the same. If you look at that, you'll start to understand when you're first learning decimals and you're trying to build it off of what you know from before, that is confusing as hell, right? Understandably. Okay, maybe. But of course, at this point, when you're teaching them decimals, they've already gone through fractions. So can somebody tell me, how would you help a student see what that is by using fractions, to see that those are actually equal? What would you do? Yeah, if you wanted to show a student those are the same thing using fractions, what would you do? So a really good guess would be rewrite each one as a fraction, right? Start there. So what's this as a fraction? 10 over 100. This, of course, would be 100 over 1,000. And then, of course, at this point, they understand how to reduce fractions. Okay, I like it. So that's a nice way to kind of like, you got the visualization that shows that they're equal, and then you got the actual fractional way to show that they're equal. If I want to start talking, so this, if I use a flat, that's a great way to get out to the hundredths place. Obviously, if I want to get out to the thousandths place, I would have to use this dude, right? So what would 1/10 of this be? What would 1/10 of this shape be? Let me come out here for you guys. 1/10 of this, right? Yeah. Literally it's 100, right? But the shape would be a flat. This sucker hat is made up of 10 flats. So if I have one flat, that is 1/10 of this, correct? Like it. Okay. So, and that's sort of like showing you that 100 out of 1,000 is still 1/10. So 0.1000 is still 0.1. So you can just step up in dimension. Now, if you want to go beyond that, you'd have to go to freaking 4 dimensions. That's exceptionally freaky. I don't care what age you are, right? That's when you start getting into something called the Tesseract, which I know the Marvel Universe took for themselves as a hypercube, right? The hypercube, sorry. So if you want to freak out, you can look up hypercube on Google. Okay. Oh, I did want to show that. All right, I already did that, good. Yeah, maybe I'll show you some videos here in a minute, yeah. Not right now. Just turn it off. Okay. So let's talk about what we just sort of kind of brought up. If I ask a student which one of these is bigger, what's the obvious mistake that you might expect some students to make? Yeah, because they're going to focus on 38, right? So this is why it's really important to build up the idea that you can start throwing zeros in wherever you want to. You could also, of course, always bring this back to fractions. So what is this as a fraction? 38 over 100, good. And this, of course, would be 4/10, right? And then at this point, they'll understand how to compare fractions. The easiest way to order fractions is to make all the bottoms the same. If the bottoms are the same, everything kicks ass. So this entire process that they already know from fractions immediately plays into what you do with decimals, right? Okay. So now the problem becomes very easy. Okay. So I see people making this kind of mistake at very high levels of math. Right, because again, it's something you don't really play with a lot directly. You don't do much with it by hand, so the minute you have to do it by hand, it's not right there. So what symbol would I put in here? Yeah. So what's kind of funny, I've actually never thought about this way before, and I have to look up the history of this to be certain, but I'm almost certain this is why the symbol is the way it is. On a number line, who would lie to the left of who? Like, which side of each other would they be? For sure. Where would 0.38 be? Where would 0.40 be? So if I put 0.38 here, where's 0.40? It'd have to be over here, right? It's amazing. So one way to look at this is from 0.40, you have to go that way to get to 0.38. Right? So it's sort of like there could be other, and I need to look up the history of it. So 0.40, 0.38 is to the left of 0.40. Anyway, okay, so you can always come back to the number line for these. Oh yeah, we did all that. So let me go back to this from earlier real quick. If I had this fraction, yeah, is that one that would be a terminating decimal if I made it a decimal? So don't divide it, just would it be? How can you tell if you just by looking at it? What was, to be a terminating decimal, what factors did you need on the bottom? Only 2's and 5's. What's 16 made of? Yeah, it's made up of how many 2's? 4. So the funny thing is, this actually becomes a way to know exactly what to multiply by to make it a perfect decimal. I've got 4 2's on the bottom. So how many 5's do I need to multiply by? 4. Each 2 I want to pair up with a 5 to make it some multiple of 10. Does that make sense? So then I actually have to multiply top and bottom by 5 times 5 times 5 times 5. So in the bottom, I'm going to get 4 groups of 10. So I'm going to have 4 zeros. On the top, I'm going to get whatever 3 times 5 times 5 times 5 times 5 is.
Does the fraction at the bottom, does that have to be a multiple of 5 and 2, or can it just be 1?
So it needs to be able to become an equal number of 2's and 5's. So what does that mean? If it's reduced and the bottom has a factor of 7, it's got no chance. So if the fraction starts and it only has 2's and 5's on the bottom, some number of 2's, some number of 5's, then you can always multiply it up to become some number of 10's on the bottom. Does that make sense? So that would be a terminating decimal right there. I lock it. Is anybody doing that? What is 3 times 5 times 5 times 5?
1,800.
There you go. What is that as a decimal?
0.1.
Yeah, and the really cool thing is 1, 2, 3, 4 zeros, so you move it back 1, 2, 3, 4 times. Also, you know it's supposed to be less than 1. What else makes sense about this? What if this was 4/16? What would that be? 4/16. What would that be as a decimal? 4/16. 0.25. So it makes sense it's a little less than 0.25. Key guess. Okay. So that's some basics of fractions. I really like to get students to understand that we've chosen a base 10 number system because of this fact, right? More than likely. We weren't there, but this is a really good guess. It's because we have 10 fingers. Therefore, any number that's based on some number of tens in some way should be easy to represent in our decimal system, in our number system. And that leads us to this kind of idea. So if I had, for example, if you had what, Jeff? Let's make this 1 just to make this easier. There. 1 over 54. Could that become a terminating decimal?
No.
You can see pretty quickly it's got no chance, right? It's got a factor of 2 in it. That's good, but it also, then it has 27, right? And that's 333. It's got no chance. So it's not going to be terminating, and it could have a pattern, right? Okay. All right. And normally people feel, why do you think people are more confident with decimals than they are with fractions?
Just the way they look.
Sure, they flow right into a single line instead of ratios, right? Also, they just fit right into our number system, which is why it's a single line. What?
We work with money.
Sure, money, totally. What makes me sad as a math teacher is all of the automatic change dispensers now everywhere. You know what I'm talking about? It makes you feel better when you get the correct change when you go anywhere, because before it was a crapshoot. But that was one place people got to practice counting and doing decimals to some degree, right? I don't remember if I told you guys this about the one bowling alley at the bottom of the Fletcher Parkway Hill. You know what I'm talking about? And it's always hilarious to me that it's got like a lane is 0.99 cents per hour. Have we told you this yet? What's wrong with that? Is that even a full penny? Do you see that? Do you understand what they're trying to say? What are they trying? They're trying to say 99 cents. So either they should say 99 cents or they should say $0.99, right? And if I was more of if I had less of a life and I was more of a jerk, I would go in with a penny, put it down and go, I'm going to go pay for it now. Keep the change, right? All right. But that just kind of shows the general populace making really simple mistakes. And normally it's percentages. Percentages are the worst, but decimals and fractions, people don't work with them very often. So what do you guys, all right. Going back to what we've done in the past about mental math. Can you guys come up with a couple of ways to do this in your head? So I don't want you to write it 8.5 times 6 and then start doing the algorithm. No. I want you to be able to do this in your head. Does anyone have any suggestions? Okay, start with 8 times 6. So I'm going to put down suggestion A. So you do 8 times 6, sure, which is 48. So I don't want an estimate. I want to know the answer, right? So then what can you do from there?
This might be wrong, but is it 6 times 0.5?
Yeah, good. So what you're really doing here is you're doing this. 6 times 8 plus 0.5, right? So 6 times 8, let me put this down here. 6 times 8 plus 6 times a half. So then that would be 48 plus half of 6. 3. Yes, right. Does anyone have a different way to do that? You're like, that's good, dude. What do you mean? We got one way. Who needs more? 8.5 is perfectly half of a whole number, right? Do you guys agree? Anything 0.5 is half of a whole number. Do you guys agree? Whatever you say there, math boy. Okay. What is twice 8.5? Anybody know? It's 17. So the shortcut to that is you double 8 and then you add 1, because twice a half is 1. So this is 17. And of course, I have a 6, so don't I just break it up like that? Does anyone remember what that's called, what I'm doing? Taking a 2 from 6 and giving it to the 8.5. It's not the best example of this, but oh well, too bad. Does anyone remember what that was? If somebody takes something from them and they give it to you, what is that? Compensation. I love it. So 3 times 17, sure enough, 51. Okay, I lock it. So it's another way to kind of do that. What about, this one's a little bit more straightforward. What am I on? Who knows? No one knows what you're on. 2.3 plus 5.4 plus 7.7. What would you do to make it easier in your head, and just see if you remember what you're doing, what it's called? Yeah, do these numbers kind of go together for some reason? Right? So 2 and 7 is 9, 0.3 and 0.7 is another 1, so that makes a nice 10. Does anyone remember what that's called? It actually starts with the C again. Compatible. I like it. They're compatible. Right? So these two make 10, and then adding from there, easy as shit. Now let me ask you, go ahead, Brian.
Oh, no.
Okay.
I'm sure.
Gotcha. That was a complete fake out. What if okay, real quick, I'm going to ask you to do something, and you're all going to really enjoy the fact that I've just asked you. Can you all add for me 7.1496 plus, what, Jeff? 100.192 by hand. What rules the day when you're adding decimals?
The decimals have to be lined up.
According to what? Sorry, you sort of said it, but I want you to be more explicit. What has to be lined up?
The placements?
Okay. But there's one thing, if I just line up one thing, everything falls into place. Decimal point, right? So I'm going to I always put the bigger number up top just because. Does anyone know why this is necessary? Now, on one level, it kind of makes sense. This 100 something plus 7 something should be 107 something. But that's not good enough of an explanation of why this has to be true.
If it was in a different place, it would mean a different number.
That's true. So that's what I was just saying. Like, it wouldn't come out to be like what we would estimate it to be. So it would be kind of like, well, that's not right. What does 0.1 here mean? Tenths. What's this 4 here mean? 4 hundredths, right? So lining up the decimal places is a form of like terms, right? So I can only add tenths to tenths, hundredths to hundredths. And I know I'm making a big deal out of it, a little thing, but it's not a little thing. This is not immediately obvious. I mean, what do you think happens to a student? They're going to do this. 7.1496, 291.001. And then, right? Why wouldn't they? That's what they've done forever. Right? So it's funny, before you ever touch algebra, there's a huge reason to discuss like terms. The first place you normally think of like terms is algebra. X plus y you can't do, but x plus x you can, right? Because they're like terms. But fractions and decimals, they are completely built off of like terms when you're adding, subtracting. Okay, I like it. While we're talking about it, let me do something a little bit earlier than we really need to, but I just want to see. How would you do 1.23 times 0.05? Actually, make it 0.5, sure. How would you line that up if you had to do it by hand on paper? Does the decimal place have to line up now? No, right? And that relates to this. Can you do, let's see if you guys are cool with this. Can you guys do x plus x squared? Can you add x plus x squared? If you can, you gotta show me, because you can't. I can do x plus x, because that's 2x's. I can do x squared plus x squared, that's 2x squared. X plus x squared, I got an x and I got an x squared. I can't put those together. Are you with me? So adding, subtracting is very restrictive. It can only handle if you got exactly the same kind of stuff. What is x times x squared? X cubed. Multiplication, more laid back. It still needs the basis to be the same, but it's a lot more laid back than adding, subtracting. Does that make any sense to you guys? So if I were to do this by hand, wouldn't you just do 1.23 times 0.5? You don't have to line it down. You could, but that would be silly. You don't have to. Do you remember what you actually have to do, though? So let's see. 5, 1, 1, 1, 6, right? I always love it when I do that and I don't do it right. It's so exciting for me, but I think I got that one right. What do you have to do from here?
Understand where the decimal point should be and how many decimal points you have for each.
So in this case, where should the decimal be? If it's right here right now, I should move it back how many times?
3 times.
1, 2, 3. Why? Why does it work like that?
You still have to take the place values into account, regardless of it being multiplication or division.
Exactly, you do, but why? I know, you're all like, dude, what do you want from me? So watch this. When you teach decimals, you're pretty much going to want to find, in fact, in general, when you're teaching something new, you want to connect it to something they've worked with a lot before. So with decimals, what I've done right beforehand is fractions. How do I write 1.23 as a fraction? Yes, beautiful. I love it. You could do 1 and 2300ths, but it's the same as this. So whatever the last digit's in is the place it's in. So it's 1 2300ths. What's this, of course? Well, don't reduce it. So what is it? Don't reduce it. It's 5 tenths. Right? Now real quick, you moved it back how many times? 1, 2, 3, correct? And sure enough, on the top you're going to get 615. On the bottom you're going to get 1,000. And divided by 1,000, you move it back 3 places, right? So that's why, bless you, just counting the number of decimal places you have is the shortcut. That's actually what's happening in the background. There's no reason a student's going to understand just looking at this damn thing why just counting works at all. So that's what you want to build it off of, something they're already used to. They're used to fractions. Okay, okay. So to me, I think if I were teaching elementary school, the biggest challenge for me would be putting myself where my students are. Because especially since I've taught college forever, I have certain things I just sort of like don't even think about. And I just sort of assume people know what I mean and so forth. You guys kind of with me. So it's like you really have to reanalyze why things work the way they do. You're so used to doing certain things without even thinking about it. Let me ask you this: what do you think about? I used to ask this question: is like, has anyone ever been a waiter or a waitress? Has anyone ever been a waiter or a waitress? I like you're answering this question like this.
Food runner, so like.
Say again.
I'm a food runner.
Food runner. So like.
Serving.
Oh, I got you. But you're not like the waiter. You take the order, but you don't take the order. You just take the order. Okay. So like tipping. Tipping used to be more of an issue. I think almost everywhere now they actually tell you what 15% is, if I'm not mistaken. They didn't used to. And that really sucked because number one, some people honestly didn't know math, so they were given the wrong, and then number two, some people hid behind people not knowing math so they can give shitty ass tips, right? And real quick, everybody should make a living wage, so what the hell. But anyway. So I used to talk about how, as a waiter or waitress, how do you estimate the amount of money you should expect to get on an order, right? And there were some people that had all these different ways that they developed just because they had to work with it. Anyway, so that doesn't happen anymore because now it tells you what the 15% should be. And now I totally forgot where I was going to do. Oh yeah, this one. So this kind of relates, but not really. But if I wanted to do this problem, there's a very specific way I could do it. What do you guys think? Is there a decimal in there that's a nice, well, there's only one decimal there, so. What is 0.25? 1/4. Is there something happening at 2 o'clock? I don't know. So this process, not surprisingly, is called equivalent fractions. So when you have decimals that are equivalent to certain fractions, and you have numbers that those numbers want to work with, obviously you're going to do it that way. So what would this be? This is beautiful. 221. So that is much easier than that would be. Oh, okay. Okay. What about this? 0.2 times 5,025. Do the same thing. 1/5, good. So that's 2/10, which is 1/5. And what's nice about that is 5 goes into all this stuff. So what will it be?
1.
Yeah, I like it. 5 goes into 5010, 5 goes into 2505, so 1005, 1005. Kick ass. So that's appropriately named equivalent fractions. So when you're working with decimals and there's an equivalent fraction to the decimal, that might make it easier to work with. Oh, okay. Last couple things, and then we'll follow everybody else who's already left. So one of these is kind of related to something we've done before. Well, maybe not. No, we haven't done this. I'm thinking about a different class. Does anyone know kind of what that represents? Has anyone ever seen that kind of object before? That kind of, do you guys remember what that was called? It's in a certain format. Scientific notation. For the problems we're doing, you don't have to look at it like that. That is just a math problem, which is really all scientific notation is. So help me out here. Can you write this as a decimal? What place is that in? Thousands. So it'll be 1375 over 1,000. Real quick, I want to point this out. Isn't that a number bigger than 1? Therefore, the fractional equivalent should be top heavy, right? So that's a nice, quick verification. You got that right? And then 10 to the 6 would be 1 followed by 6 zeros. As I was talking, okay, good. I counted correctly. So multiplying decimals by powers of 10 should be easy because they both flow in our base 10 system. So how many zeros cancel? You're actually canceling 10s, but you can look at them. So I can kill 3 zeros, right? So then I just get 1375 0, 0, 0. Kick ass. And if anybody knows scientific notation, does anyone know what that number tells you to do? Yeah, move it over 6 times. 1, 2, 3, 4, 5, 6. It's the same number. All right, sweet. So that's the nice thing about scientific notation. It's not just a way to represent a number. It's actually a problem that works out to be the number it represents. You're back. Okay. Last thing we want to talk about. And this is some people's favorite thing, meaning, no, not really. Rounding, right? Let me just jump right into the major issue. Let's say I want to round this to the, you can do it, Jeff, hundredths place. This kind of, I'm not going to ask it this way. I could say, what number's in the hundredths place? But, you know, hundredths place is right there. Is that cool? All right. So, of course, how do you round? You first identify the place you're supposed to round to, and then you look the next number. Now, what I see people do is this. People will do this. Well, that 7 makes that become a 5. Then that 5 would make that become a 5. And then that would make that, you know, no. I'm not talking about these places. That 7 cannot suddenly magically make that a 5. That is a 47. That is, you kind of with me? So like 4,447 is closer to 4,000 than it is to 5,000. You guys see that? So a nifty way to look at decimals is to sort of ignore the fact that they're decimals sometimes, right? That is 4,447. That is closer to 4,000 than it is to 5,000, so the answer will be 44, right? But do you understand what I mean? I call this like dominoes. This makes that become a 5, which makes that become a 5, which makes that become... No. It doesn't work that way. Okay, I'll lock it. What about this? Here's the other weird thing. What if I give you this, and I want you to round it to the tens... no, to the hundredths place. Yeah, same. For some reason, this sometimes freaks people out. Does anyone know what that would be? Yeah, well, yeah, exactly, 0.2. And just to really make sure, you could put like a 20, just to show, hey, I did it to the hundredths place. People freak out about it because, and I don't blame them, because I didn't round, and that's the tens place, but 19.8 is obviously closer to 20 than it is to 19, right? Okay, those are two places I see people make mistakes. Beyond that, the rounding should be familiar to everybody, so that shouldn't be too big of a deal. I don't think there's anything too special about rounding to talk about. No, okay. No. All right, so that's plenty. We'll follow everybody else. So on Thursday, I'll have the quizzes graded. The next test this week has been hellacious. By the way, quick note for you future teachers. Do not schedule every quiz and test in the same week. Oh my shit, I've done that to myself. This week is that week. Good. Our next test, I think, is a week from Thursday. Is that true? Yes? 16th, that's right. This Thursday is the 9th, so a week from this Thursday. So on Thursday, I'll have the practice test. Next Tuesday will be review day for the test. Okay.